So now the next step is step number 3, calculation of shear at the base. So step number 3, calculation of shear at the base. Now earlier we have gone through the table number 10 and table number 9 from page number 35 and 36, and the next table is table number 11. We will get the coefficient, that is on the page number 37. So I can write here from table number 11, page 37, that is IS 3370, part 4, 1967. So here again same, you will get the coefficient, and that coefficient is based on your h square by dt ratio. So therefore for h square by dt, which is equals to 10, so coefficient you will get that is for the triangular load is found to be 0.158, and that is positive 0.158. So what does this positive sign indicate? So positive sign indicates shear is acting inward. So shear is acting inward, and that is the reason it is positive. So again on the same page you will have the formula for calculation of shear, and that is equals to coefficient multiplied by W into h square. So coefficient is 0.158. So this is going to be 0.158 multiplied by 9.81. Now here the unit is different, of W unit is different, and that is the reason we can calculate this. And if you calculate coefficient multiplied by W into h square, that is coming out to be 24.77 kilonewton. So this is the value for shear at the base. Whatever is there, hook tension, moment, and the shear, we are calculating from the IS code. Coefficient we have calculated, and then we have gone through the calculation of particular hook tension, moment, and shear. Now similarly we'll go for the step number 4, that is design of section for cantilever action. So we can write down here step number 4, that is design of section for cantilever action. So in this problem the thickness is already is given, or already it is to be assumed as 160 mm. So we can check the cover as 35 mm at the center of the reinforcement. So we can write down providing cover of 35 mm. So therefore now you'll have the effective thickness and that is equals to T minus T dash. Let us have this is as T. So T minus T dash, so which is 160 minus 35, and that is equals to 125 mm. So now we need to calculate the area of the steel which is required for the cantilever bending, and that is given by area of the steel for the cantilever action or for the cantilever bending, because we need to calculate two different area of steel for hook tension as well as for the cantilever action. So here AST is equals to divided by sigma ST into J into T. Now this J factor, that is the lever arm factor, then you have this D, that is the effective thickness. You may just consider the effective thickness, and you can consider here moment at the base, right? So sigma ST you can just consider for M20 grade of the concrete. For M20 grade, you know that sigma CBC, which is equals to 7 Newton per mm square, and modular ratio, that is 13, and from that you can get the neutral axis depth factor, or K. So this K is equals to M into sigma CBC divided by M sigma CBC plus sigma ST. Now this sigma ST, that is 115 Newton per mm square, for M20 grade of the concrete. So here we can just calculate this. M is 13 multiplied by sigma CBC, that is 7. 13 multiplied by 7 plus sigma ST is 115. If you just calculate this value, so here you will get 0.442. Now here lever arm, that is J, which is actually 1 minus K by 3. That is the reason we calculate first of all K, and this 1 minus 0.442 divided by 3. So if we just calculate this, J equals to, you will get 0.853. So you got now sigma S T, J and D. M is already known. So if we just see it again, the formula for AST, that is M divided by sigma ST JD, and for M20 grade of the concrete you have the sigma CBC 7 Newton per mm square and M modular ratio 13. Now here you know that K equals to M sigma CBC divided by M sigma CBC plus sigma ST, and if you just calculate this value you will get 0.442, while J, that is the lever arm factor, and this lever arm factor, that is 1 minus K by 3, and you will get 0.843. So finally you will get AST, that is moment. You already know moment, we already calculated 7.65 kilonewton meter per meter. So 7.65 into 10 raised to the power 6, if we just convert into Newton mm. Then we have sigma ST, that is 115 multiplied by 0.853 and multiplied by 125. So this is coming out to be calculation after. Around 670 mm square. So this is what you will get area of steel. So once you got AST, you can write down using 12 mm diameter bars. So if you just make it 12 mm diameter bars, so area of one bar, that is equals to so you got here area of one bar, which is actually have 4 into 12 square. So if you just calculate, you'll get it around 113 mm square. And therefore you can calculate now spacing. So spacing equals to area of one bar divided by total area multiplied by 1000. So 113 total area you got 670 multiplied by 1000. So you will get it spacing of around 160 mm. So you can make it 150 mm as well. So we can write down providing. So therefore providing 12 mm diameter bar at, we have to round it down, so instead of 168 we'll go ahead with the 150 mm, center to center, and that is to up to height of 1/3 of h, or you can say h by 3, that is equals to 4 by 3. So it is around 1.39, or you can say 1.4 meter. 1.4 meter from the base. And then this is 150 mm, and then rest of the bars you can provide it with the double spacing, or you can say it is called as the curtailment. So you can write down providing 12 mm diameter bars at 300 mm center to center for remaining. So this is about the calculation of the design of section for the cantilever action. So we'll see the next step in the next video. Thank you.